All right, short presentation on Chapter 14 in Electronic Fundamentals textbook on transformers. We've covered Chapter 14 a little bit in the past, either in EC 1 or 2. Mutual inductance. Inductance is, the opposition. Inductive reactance is the opposition to current flow in a circuit created by the inductance. When we put two coils, close to each other, magnetize one, place power on it so it becomes magnetized, it'll create a magnetic field in the second one, creating a voltage. That's the basic concept behind transformers. We can figure out what mutual induction is, and using the coefficient of coupling and the inductances of the two coils of wire. Coefficient of coupling is dependent on how the coils are oriented to each other, the proximity to each other, how close they are, and then if they're wound on that common core, or if they're just two coils placed next to each other. The amount of mutual inductance is certainly important when we look at the simple transformer. And here we show a basic transformer just with two windings. The schematic symbols are there. The one without any lines is considered to be an air core transformer. With the dashed lines, it is a ferrite core. And then by far the most common is the small one, or is the one on the right with the two solid lines. That constitutes an iron core transformer. Iron core is used, soft iron is used because it is easily magnetizable and also loses its magnetism relatively quickly once power is removed. Two basic types of transformers, step up versus step down. Step up, very simply, secondary voltage is greater than the primary voltage. By far more common, the step down transformer, secondary voltage is less than the primary voltage. Utility tends to send the power on the power lines at a very high voltage, or at least at higher voltages, so that they get less I squared R losses. And then transformers, it is stepped down to voltages that we can use. Example here, we have a transformer with a 4:1 turns ratio, 120 volts on the primary. It means there would be 30 volts available on the secondary. Again, turns ratio is 4:1. Isolation transformers, special type of transformer with a 1:1 ratio, same voltage in as out, used to isolate one circuit from the other, helps to stop DC from being passed through while maintaining the AC path. Also used to isolate equipment from surges and swells on the power lines. We keep talking about power. The basic premise of a transformer is power in equals power out. This is only true of ideal transformers. And realistically, we know from past experience there's no such thing as an ideal transformer, no such thing as an ideal inductor, an ideal capacitor. Same thing with transformers. There's no such thing as an ideal transformer. In transformers, we do look at them as ideal and use these formulas. And there again, the big concept here is power in equals power out. So voltamps on the primary side should equal the voltamps on the secondary side. So using, again, the bottom one is our turns ratio formulas. We use cross multiplication there. We can figure up any of the voltages or currents if we know, three of those four items. In real life, again, we know transformers are not ideal. Actual transformers have several different losses. First is the windings resistance. Again, we know anytime power flows through a wire, that resistance creates heat. Heat is a form of loss. We have hysteresis losses. The slide says, due to the continual reversal of the magnetic field. If you think of the way the magnetic field, aligns, when you, reverse the current through that same coil, those magnetic fields have to go the other way, and they have to align the other direction. And basically when they're bumping into each other is our hysteresis losses. Similarly, eddy current losses or core losses are those created by the current going back and forth through the core, again turning back and forth. Hysteresis loss and core losses, hysteresis and eddy current, are probably the two greatest losses we see. Then flux leakage, talking about the magnetic flux lines. Not all of the magnetic flux lines from the primary, where we're providing power, go into inducing current in the secondary. Any of those magnetic fields that are lost are considered flux leakage. And then the last thing to talk about is the capacitance. And again, we've talked about capacitance before. Anytime there's two conductors separated by an insulator, we have some capacitance. And if we look at the windings of a transformer wrapped around a common core, they're all right next to each other, so there's going to be some capacitance and some capacitive loss there. Efficiency can be calculated. We know that there's all those losses, and like we said, no such thing as an ideal transformer. So just to look at the power out divided by power in is going to give us an efficiency figure. We multiply times 100% to put it into a percentage, so we know how efficient the transformer is. Example here, efficiency of the transformer, 120 volts times 20 milliamps would be about 2.4 watts of power. Secondary side, 15 squared would be what, 225? 225 divided by 100 is 2.25 watts of power. So 2.25 divided by 2.4 gives us about 94% efficiency. Again, if you do the calculations, it's 93.75 or 94% efficient. Some things inside of transformers. We do have tapped and multi-winding transformers. Tapped transformers, like they show here in the illustration, we have a transformer with the primary for a single voltage and the secondary center tapped to provide, say, 120, 240 on the secondary side, say for your house. A utility could put in a transformer like this if they knew exactly what your voltage was going to be coming in on the power lines, and then put 120, 240 into your house. The taps can also be on the secondary side or on the primary side. Now on the right side there, they show the primary having multiple windings and the secondary being a single coil. This could be for, say, 240, 480, or like it says on the slide, 120, 240 on the primary coils, and then provides us, say, 24 volts on the secondary for control power. Very common, small transformers have small control transformers have dual windings on the primary like this, so that we can hook it to 240 volt systems or 480 volt systems. Here's an illustration of what we've been talking about. Say for the transformer outside your house, utility puts it up on the line, and they've got 7,160 volts coming in instead of the 7,200 that they're indicating on the slide. They can move on to one of those other taps to make sure that the secondary side you get 120, 240 or as close as possible, inside your house. And so they might have to go down, one or even two of those taps to adjust that. Then the last thing to talk about is three-phase transformers. Three-phase power we've talked about before. Comes delta or Y. In the delta setup, we have straight voltage. In the Y setups, we have voltages determined by the square root of 3. So 120, 208 is a three-phase Y voltage, 480, 277, whereas 240 three-phase or 480 three-phase are straight delta setups. Again, it's still power, so it can be transformed. We just need 3 windings to do it. Transformers, three-phase transformers can be delta to delta, Y to delta, like illustrated on the on the slide, or delta to Y. Again, the slide does say, it's generally used for step up cases. I don't know if I necessarily agree with that. They can be used either way. We have a delta to Y transformer, in the college here that goes from 480 volts that we use for some of our HVAC equipment down to 12208 that we use for almost everything. We have 120 volts throughout the facility. And so that basically wraps up entry-level, transformer talks. We're going to do some more with transformers and work on some labs so that we can hopefully get a better understanding of everything to do with transformers.